I couldn't make this workshop last year, but it's a great pleasure to be here this year. This is a fantastic intersection between communities that only interact generally peripherally, and that is great to see. I've been working in hardware acceleration of sparse cognitive algorithms. In fact, I'm one of Dan Hammerstron's seedlings. We've been going for 6 weeks, so I don't have a lot to report. In fact, I can go straight to the conclusions if I wanted. But what I will do is talk about some of the other work that we've done that feeds into this, and also talk about what we're doing specifically within that seedling. But I've been interested in emerging devices, so there's no emerging devices here, emerging architectures, and particularly artificial intelligence and how to build machines for artificial intelligence for a number of years. And this led a number of years ago to one project where I did a chip for hardware for speech recognition. This started about 10 years ago. And though commercial grade, and my reasoning here was a set of algorithms that were really beginning to work very well, but we're straining a computer in order to be able to do these things efficiently. So can we do hardware acceleration of them in order to improve them? And though these algorithms are not directly neural inspired, of course they're indirectly. Hidden Markov model, of course, is a Bayesian probability calculations. So there's a strong neural element here, even though they wouldn't be considered part of the neural community. And we built hardware for this. Actually ended up being a mixed hardware-software system with some of the hardware, for example, the CNOME scoring and first pass of word scoring being done in hardware, but the second pass of word scoring being done in software. And the reasons for this were purely commercial. You had to retain enough flexibility to tune the algorithm to the end application. And this was driven by our then industrial sponsor in this. And in fact, this is productized, and it's in automobiles today, which is very pleasing. In fact, my wife has one of these cars. And we were out driving the other day, and someone cut her off, and she yelled out, "Idiot!" And it turned on the voice recognition system, and it said, "Calling Paul Franzon." So this demonstrates 400x improvement in power per unit performance, which more than justifies building a hardware accelerator. But now we're seeing the success of cortically inspired algorithms. They are starting to have commercial traction and traction within the defense community, which of course is relevant to my funding source and to me, being an ex-Army officer. And once I started seeing these, particularly in the Mentor HTM, AFL's use of cogent confabulation, and other temporal algorithms are out there when we're interacting with other people using building things on temporal algorithms, we started thinking, well, what can you do to accelerate these? But it's actually a very different problem than accelerating the voice recognition algorithms I was talking about earlier, because as you'll see in a moment from some of our preliminary results, these are very memory and interconnect bound, particularly at the scales at which we want to build them. But I still feel that there are very strong candidates for hardware acceleration, but just not a point accelerator, which is what you normally think about when you think about hardware acceleration, such as that voice chip that was only a couple of square millimeters of silicon in the end. So some reasonings for general trends in the silicon world that justify the approach we're taking. This is a plot from a blog-style source, but nonetheless is accurate. This shows the gap between CPU performance and memory performance over time. CPU performance grows at Moore's law rate, 60% a year. Main memory performance, at least traditionally, grows at a performance rate of 7% a year. And part of the reason for that is they have to increase capacity as well as performance. But there's a big gap here that grows at 50% a year that really makes it difficult to build a system that needs a lot of memory bandwidth and a lot of memory and have it operate efficiently. At the same time, and this is part of the reason, on-chip bandwidth versus off-chip bandwidth has a similar, very strong divergence. Again, On-chip bandwidth scales with Moore's law, doubling about every 16 months. Yes, that is slowing down as we reach the end of the roadmap, and we can no longer scale lithography efficiently, but it's still accelerating quite a fast rate. In contrast, off-chip bandwidth used to double every 28 months, and now it's every 4 years as we reach the limit for pitches for flip chip solder bump, and we're operating the circuits as fast as we reasonably can. And so we get a many orders of magnitude gap that is also growing very fast. This relates to the previous slide. It's one of the causes of the data on the previous slide, but in itself is also a big limitation when you want to build a system-level performance beyond the scale of one chip, because this is a very serious bottleneck. As several authors have mentioned, power consumption is very important, and as for example Steve mentioned, it is the key metric that one should look at when considering computing. And earlier last year, we finished a detailed study where we developed the best research state-of-the-art energy per operation for quite a very wide range of operations, collected them together and scaled them to the 7 nanometer node using conservative scaling factors from Intel. And this is the results of that. So 1 picojoule per op is the same as operating 1 milliwatt when operating a gigabit per second. The thing I want to emphasize here is that the floating point unit down here at the end of the roadmap operates at less than 1 picojoule per 32-bit floating point operation. And in fact, even today, in today's technologies, you can do this at a few picojoules. And in contrast, it is moving energy around. Interposer here means a really energy-efficient interconnect structure. And moving around the memory hierarchy, this is the end of the roadmap, 16 nanometer DRAM, and this is just the DRAM core. This does not include the I/O. Similarly, for caches are terrible as well because the associativity and big line sizes. Moving data around, particularly moving around a memory hierarchy, is very energetic. And so my point is here, this is not the place to focus. Getting this down further, for example, doing the equivalent of an 8-bit flop in something else, and I'm not going to get terribly finger-pointy here, just whittles this down a little but keeps this all the same. And you don't do equal numbers of these, but you, as you scale things with Moore's law, your energy ends up being increasingly spent on moving data around and dealing with memory. And they're the key things you have to deal with in order to build an energy-efficient computer, no matter what it's doing. So, as mentioned, we were a seedling as part of doing a study in Dan's program. Our goal specifically is to establish the potential for hardware speed up and power reduction, mainly of 2 algorithms, HTM, Numenta's HTM, and SPASI, which I can't talk about a lot, but is a similarly inspired algorithm. We've just finished a GPU baseline, and we're doing an architectural study. And as Winfrey pointed out, the big counter challenge here is preserving algorithmic flexibility, and for me, of course, also ability to scale, actually for both of us. And this is a little bit of a tension, which I'm going to discuss how we're resolving. Because these algorithms are evolving, it's not necessarily clear which features will end up in something that might be final, and so forth. We are looking at a couple of applications that are only on the side, and I'll describe these at the end. They're more benchmark drivers than true application drivers. And we are also interested in other algorithms that have had some success. For example, where Air Force Research Labs has been exploiting cogent confabulation in a number of their applications. And that's been interesting, and we've been monitoring that work. And part of my goal at this meeting is to collect other algorithms. So I'll hand around a plate in a moment which you can put your algorithm on. But no, seriously, I'm very interested in algorithms that look like that are going to have real traction. So we actually just finished a GPU version of SPASI and HTM. We haven't finished profiling it yet. And in fact, these were numbers that were emailed to me this morning. But nonetheless, they show the limitations to some degree of performing these very distributed, large-scale algorithms on even GPU hardware. And this is not one GPU engine. This is a GPU array, a GPU supercomputer, if you like. And that is, you can see in both of these, the communication function, which is essentially the same, either communications or weight summation, consumes most of the compute time. So this is interconnected memory again, is your bound on these systems. And also point out here that SPARSI in particular, which is a substantial algorithm in the sense that it tends to need lots of memory, does need a lot of memory. So these algorithms, particularly SPARSI, can benefit from large capacity as well as large memory bandwidth. We're going to do a lot more profiling from these implementations to understand the speeds and feeds, as us engineers call it, better. But this is indicating to us already that my supposition coming into this will hold some ground. Some other work we actually did last year before getting started with what we're doing now with Dan was Wei-Fu Lee did some early work on building an HTM ASIC. It's hardwired to one application, so it's not meant to be indicative of where we think we'll end up, but at least shows potential. I'll come back to this slide, but the application is a handwritten figure identification, which is explored by others for HTM in software, but is a good application for HTM. HTM, with a relatively small amount of training, gets good recognition rates on this in different data, in the MINS database and the US Postal Office database. But Wei-Fu built an ASIC with a set of nearest neighbor communicating cores. Here, this spiral communications pattern, as you can see there. And he actually synthesized this to a 45 nanometer library. And he ended up for a column, equivalent of a column in the HTM algorithm, with power of 1.3 milliwatts, which was 10,000 times less than software, and up to a 676x speed up over software, and this is in 0.01 square millimeter of silicon. This represents a combined performance per unit power of 10 to the 6 over software, but again, I say hardwired for one application and a relatively small one at that. So particularly Dan, don't hold me to that as an end metric. But it indicates the sort of potential that you have here. This is way beyond what you could achieve just with simple Moore's law scaling of conventional computing, way beyond. And the architecture is fairly simple, and this was a nice result he generated last year. This again is the application, and just pointing out the ranges. There was a range of speed ups. I chose the best one. It depended on the particular example that you ran from 300x to about 600x. So one thing that we're exploiting this, as others have mentioned, emerging and coming quickly mainstream technologies in 3D IC. There's a number of technologies that come together here, putting two chips together with a high-density microbump layer, for example, through silicon vias, which are exactly that, vias that go all the way through a silicon chip, and what are called interposers, which are really taking the back end of a line interconnect and building large substrates from that for connecting chips together. Nice thing about this set of technologies, they're fairly mainstream. You can buy them with a purchase order, and if you manage things right, you don't have to buy an entire wafer full of stuff, which in a university budget, as discussing earlier, gets very expensive very fast. So we have built, and are continuing to build practical things with reasonable technologies in a prototyping mode using these 3D technologies. Some work we've done in the past. This is a past DARPA effort. This was for radar processing. We built an FFT engine where we have an array of SRAMs integrated with the floating point units. This is the die photo. We get a 60% power savings, but more importantly, a 100x increase in the memory bandwidth by using the 3D technologies. We had over 1,800 pins to the memory in this case. In another project, we built a complete synthetic aperture radar processor using a logic on logic partitioning in 3D, again the dye photo, and we get 22% improvement in performance per unit of power. And these are relatively simple exploitations of 3D. In one project now, we're sponsored largely by Intel. We're looking at heterogeneous computing. We're taping this out in May. And what we're doing here is integrating two different CPUs together with fast thread transfer between them. We're in addition taking on a SIMD core from another DARPA project, integrating these on an interposer, which then integrates with a fast Tezeron memory, which they call the DIRAM 4, which stands for disintegrated RAM. I don't know what happened to numbers 1 through 3, but it stands for disintegrated RAM, which is a very interesting memory. Took some public domain information about this memory for this slide. It is a 3D memory. It's a 3D stack in itself. There's 256 channels. The memory banks are quite small, which gives you a very fast latency, about 4 times what you'd normally get with DRAM. And thus you can get a very large peak bandwidth, also having a substantial amount of capacity as well. This is a 3D memory that we find very interesting and exploiting in this project and plan to investigate its exploitation for cortical processing. So in the cortical processing project, we're investigating a variety of potential build approaches. Again, largely digital, per my earlier argument, and focus on different points in the flexibility versus power and area cost. So I described an ASIC version aimed at one specific application. But in addition, at the other end, we are looking at a SIMD processor implementation, which I'll talk about a little bit more, because that's leveraging a previous project. And in between, we're looking at something that's specifically to accelerate HTM, and a processor that is in between, which can accelerate other algorithms as well, retaining some programmability, but not necessarily the full software programmability of the SIMD processor. So this is the floor plan of the SIMD processor. I won't go through all the details here, but this is the actual multiplier array. And this is, in a sense, GPU-like, though it doesn't have some of the aspects of GPUs that tend to weigh them down. It's programmable. It has software. We're writing a compiler as well. And as is typical in these architectures, we also have a very large register file. And rather than exploiting a cache hierarchy, we tend to use static RAMs that are software managed because they're lower power. Here's some power efficiency simulation results, detailed simulation results for this, actually based on simulating an FFT application. Look at the 16-lane version here. Roughly half the power goes into the floating point units. Roughly 40% goes into the register file, and roughly 10% goes into the control, which is, we spent a lot of effort getting that down, but that's actually a very unusual result. Generally, it's the other way around. 90% of your power goes into control and data management and so forth, whereas only 10% goes into arithmetic. And through a variety of mechanisms here, we've been able to reverse that. So as I commented down the bottom here. So that's one reason we feel this is an interesting architecture for the cortical applications as well as other applications. Luther Blackwood is putting together a processor aimed specifically at the Numenta HTM classes of algorithms, and he's done a C++ implementation and a preliminary mapping onto what a chip might look like, and he estimates he'll get a 140x speed up over a CPU implementation at the scale of 10,000 columns. Just an early indication of some of the potential here for one of the other data points. Interconnect as well is also a very big issue in these when you're building hardware for these applications. You tend to need a lot of connectivity between these as you communicate information. We've already seen that communicating information takes 90% of the time in our GPU implementations, so we've got to pay a lot of attention to this as we build hardware. We've got concepts here, but we haven't started exploring them in detail yet. We actually have several different interconnect options under consideration, and we're going to use the profiling results from our GPU activities to investigate a variety of those and work out their trade-offs and relative benefits. I'm going to turn a little more to applications that we're exploring, and we're really doing this from a benchmarking perspective rather than saying, at the moment at least, that these are the best applications for these algorithms. One thing we have done in the SPARSI code is look at video action recognition, and this is running in our GPU now. The idea is to recognize different actions in video and sort those. And we've been through the process of training the SPARSI algorithm and doing recognition on these. We also plan to look at a robotics application, self-location and mapping, which is abbreviated as SLAM. To keep this simple, what we're going to do is have a set of wheeled robots that, just like Daleks, won't be able to climb stairs, and have those go around a building environment. We're going to put different QR codes at different points, and basically works out its own map of this environment based on the QR codes, rather than facing a more general problem with all its complexities. And a couple of really bright master's students have built this. I actually don't know yet if it moves, but they have built this and are investigating this application. So that brings me to the end. As I indicate, we have preliminary results that show there is high potential for speed up and power reduction over a CPU, GPU for these applications. We are investigating a variety of architectures and a variety of interconnect solutions. And scalability is very important to us. We don't want to just show this on small samples. And we are looking at applications such as really for benchmarking and profiling, such as video action recognition, SLAM and ham-spam, and some others. And finally, I'd like to thank particularly DARPA for supporting this. Google is now we have some funding from Google as well now, and our 3DIC funding was funded from these sources, particularly largely Intel and DARPA, and we very much appreciate their work and support of our preliminary work here. And I thank you for your attention, and I'll be happy to answer any questions. Thank you very much.